This material is made available to you by or on behalf of the University of Melbourne under Section 113P of the Copyright Act 1968. It may be subject to copyright. For more information, visit the University Copyright website.
And if we're in the linear region, we start getting this non-linear effect where essentially what we're seeing is this exponential type of decay in the signal. Okay. Then what we went on to discuss was, well, you know, we're making an assumption here, and the assumption is that the gate voltage is changing abruptly as a step. What happens when we have we have finite rise times at the inputs? And essentially what we showed is there's three stages of, that this inverter goes through. One, the first stage being when the NMOS is off, the PMOS is on. The next stage is when both the P and the NMOS transistors are on. And what we're seeing here is we're seeing a situation where the P device is pushing current, whereas the N device is trying to sink current. So essentially they're fighting each other. So therefore we don't get as sharp a transition as we would desire. And then what we've got is in phase 3, or the last phase, what we've got is essentially the P device is off, so no current is actually coming through the supply. And and then at this particular time, we're actually discharging the capacitor that's connected to the output of this inverter. So therefore that gave us a little bit of background. Then we went on to talk about some RC delay models and why we're beginning to talk about approximating these circuits as RC circuits, and specifically why are we doing this instead of, for example, trying to do a full SPICE simulation of a full chip. And essentially what I tried to emphasize to you was, you know, chips are getting very complex today. You know, for example, a processor might have up to 10 billion transistors, right? And, you know, if you try to put that in any kind of simulator, it just won't work. You don't have enough computing power, right? And what we went through is let's talk about these extraction methods, or these RC approximation methods. And this is essentially what you do when you're designing complex chips, right? If you're designing complex digital chips, what you do is you go through a process of you design a circuit, you synthesize that circuit, and there's sets of tools called parasitic extraction tools, which actually simulate your RC delay and extract your RC delay through the parasitic extraction tools, which then tell you approximately how fast that circuit's going to work. Okay. We went then through various gain diffusion capacitances, and you know, we worked out how to calculate the gain and diffusion capacitances, making certain approximations. And there, what we said was, for an NMOS transistor, we assume that the resistance is R, or the smallest resistance is R. In this particular case, we're approximating a transistor as a switch, where it's got a resistance R and a capacitance, but you know, at the various diffusions as C. And here we're also driving the capacitance of the next gate. So in essentially there, what we did was worked out an equivalent circuit for this. So therefore, we can actually say, well, if we've got this RC circuit, how quickly can we get it to decay or go from a 0 to 1 transition? And then in the last thing that we did was we talked about transient responses and showed how it gets really complex very quickly when you're trying to do your standard Laplace type transfer function type of approaches. And on that note, we're going to talk now about something called Elmore delay and how do we calculate propagation delay using Elmore's theory. Okay, so let's talk about it. So Elmore delay, essentially what it's saying is that most circuits can be represented by an RC tree. Who can tell me what an RC tree is? Okay, so it's essentially a network of resistors and capacitors, but what's important is in trees there are no cyclic paths, so there's no feedback paths. Right? That's what's important. And what we're also doing here in order to be able to do this is we're making an assumption that the voltage, that the root of the tree, which is where the tree starts, is where the voltage source is located, and at the leaves there are the capacitors. And essentially what we've done, or what the Elmore delay estimate or theory says, is that the effective propagation delay, and it's a very coarse approximation, but it's okay, is the propagation delay is the sum of the resistance through a particular node multiplied by its capacitance. So, yes? Yes. Yeah, you've got two. You've got this one.
Yeah, it's a line 2.
Sorry?
The propagation delay with line 2, but...
Yeah, okay, but what I've done is, you're right, there's a log 2, but what you're doing here is, I've put the log 2 there, but essentially, and we'll talk about this later on, alright, is that you try to bring in, you increase the resistance by log 2, so therefore you don't have to have this log 2 factor running around. So therefore, usually what you try to do is you try to make the resistance log 2 as large, so therefore you say that my time delay is RC, right? Or you can actually have the real resistance and say real resistance times the capacitance times log 2, right? So that's the difference between the two slides. One was the previous slide, and this is today's slide. So essentially what we're saying is we're sucking up this log, I'm sucking up this log 2, right, so that my delay is just RC. And then what I've defined is R is equal to R real times log 2. Right, that's what I'm doing. But what's important here is, other than this constant of log of 2, is that how do we put this theory into practice? Right, and the way that we put this theory into practice, if we want to work out what the propagation delay is from this source changing to this output changing, the Elmore delay theory or methodology, what it does is it says, well, you work out the resistance and the capacitance on that tree, resistance plus the capacitance. So it's all the resistors that you see. So you break this up into sections, and it's the total resistance in the path multiplied by that capacitance for each node. So for example, if we were looking at this circuit, we've got resistance times that capacitance, resistance that plus that times that capacitance. That is our estimate to our propagation delay. And this is an estimate. And for argument's sake, it's good enough for what we're trying to do. So yes, you might have, there's going to be a few % error, but for most intensive purposes, it's good enough for us to do some design and also to give us insights into how we should design these circuits. And for example, as we'll see later on in this lecture, there are some gates which are more expensive in terms of propagation delay than other gates. So therefore, even though you've learnt potentially in your second year or third year, I don't know where it is now, it's somewhere in the master's course, how to rewrite some logic functions. Really what you need to be doing is, like, for example, if you had a truth table and from a truth table, how to derive the how do you call it, the equivalent circuit. Usually, you know, have you all done Carnot maps? And right, so usually you grab, you know, the elements and you try to work out what's the equivalent circuit. But the point here that I'm going to try to teach you is, yeah, you can do that, but that's not necessarily the fastest circuit. It might be the simplest circuit, but it might not necessarily be the fastest circuit. And what we're going to do is use this in order to be able to analyze that. So this is an estimate. So what I did here is looked at the following situation, and it was, hey, let's now look as an example where I have one inverter that's driving 3 inverters. Right, that's an example. So let's go through and, you know, analyze this circuit. All right, so can people tell me what are all the capacitances and all the resistors that I would expect? Okay, so we've done this in the last, forget about that we're talking about an Elmo delay. This is just, hey, how do we approximate this one inverter driving 3 inverters? What are all the resistors and all the resistance and the capacitance in order for us to be able to work out the delay, and then use the Elmo delay methodology in order to work out what our propagation delay is. Let me see if does anyone have just a blank piece of paper that they can lend me? No. All right, because I want to go through it, so otherwise I'll be writing on the back of. All right, perfect. Thank you. Okay, so I've got this situation, right? Question. I want to make this run as fast. I want to know how fast I can make this run. Okay, what do I need to do? Calculate what? Propagation delay. Yeah, all right. So I want to calculate. I want to determine the propagation delay, right? And what we'll see actually is there might be the propagation delay for the, you know, for the falling or raising the signal might be different, all right? But we want to work out the propagation delay. So in order to be able to do that, what do we need to do? I'm giving you a hint here, right? Sorry? Right, so what I want to do is work out all the resistors and the capacitors, right? And initially I want to work out all the capacitances, right? Okay. And here when I'm drawing this, and I'm saying 2, 1, what do I mean? Yeah, K equals to 2. And what does K equal to 2 mean? It's twice as wide. Yeah. All right. So that's what I'm saying. Okay. Perfect. All right. K is twice as wide. What? Okay. And this is the output. What do I do here? And why? Okay. So what we said is the delay depends on the capacitance, right? That the capacitance, the parasitic capacitance in the circuit plus the capacitance that we're trying to drive, right? So what we've got here is we've got, for argument's sake, we're driving 2 or 3 NMOS devices. Sorry. All right. So let's say I'm driving. What does this node see if it's driving through these? How is it connected? So I want this. How am I doing is connecting that, and connecting that to there, that to there. All right, perfect. How much capacitance does this node see? All right. Okay. Well, what's the capacitance of each gate? Here, let's say the input here to each logic gate. How much capacitance do we see? We see the gate capacitance of the two transistors in parallel, right? If this is K equals 2 and this is K equals 1, what do we say? Sorry. What do we say here? This is okay. So there's a 2C up this way and down this way. C, 1C, perfect. But there's 3 of them, right? So what we would be doing is, yeah, you can multiply. Yeah, exactly, because they're all in parallel, right? So you can go 3 times 2C plus 3 times 1C. All right, okay, perfect. So this is the gates that this is driving, right? And if it was 4, what would I do? It'd be 4 times 2C, right? And 4 plus 4, all right? Just a trick question. Okay. Now, how about here? I got these 2, sorry, terrible draw. Okay. What do I need to draw here? I've got to draw one capacitor here, one capacitor here, one capacitor here, and one capacitor here. Right, so this is 2C, 2C, 2, oh, C and C. Right? Okay. Perfect. So I've got essentially this terrible looking circuit, and we know, and the reason why we've chose this to be 2 is twice as large, but the resistability is half, so if we make it twice as large, the resistance is R. Right, so what we now have is we've got, depending on which transition we're going to do, all right, we're going to have, sorry, this is supposed to be a switch here, I'm terrible at. Done. Okay. All right. This is why you should never. I thought I was going to be brave and try to do what you know. Okay. And what we see here is we've got 6C plus 3, 9C, right? So we got 9C here. Can anyone tell me why we have 9C? They're on parallel. So there was 3 and each NMOS had 2. 3 NMOS, sorry, 3 PMOS, so 3 times 2 is 6C, 3 plus 1 is 3C, they're still in parallel, so therefore that's 9C. Okay? Alright, excellent. Now, what I'm saying is we're going from a output from a, depending on if we're an input or output, but we're going to change the input from 0 to 1, right? So what's going to happen? Essentially, what we're going to have is that one's going to be open, that one's going to be closed. So our equivalent circuit is 3C plus, did I get that right? So we've got 3C plus, that's 9C. Okay. All right, so that's for our falling edge. That gives us our equivalent circuit. So we've got R and 12C, right? And you can, what I'll do is I'll let you guys go through the process of working out what it is for the rising edge. Now, what I want to make sure that you are aware of is, suppose, let me ask, the seeds would all be different. PMOS device was 4 times as large. All right, K equals 4. What would R be? R on 2. Okay. All right. Okay. So, and what am I trying to emphasize here? Right. The thing that I'm trying to emphasize for you all, again, not speaking proper English, is to say this R, when I'm looking at from a 1 to 0 transition, it's the resistance of the NMOS device, because that's what's actually on. Whereas if I'm on the rising edge, the NMOS device is off, the PMOS device is on, and that's why this R represents the resistance of the PMOS device. Right? Now, here I've chosen them both to have the same resistance, but I'm trying to emphasize that this R and this R, even though they have the same value, they're due to a different transistor, right? And that's why I wanted to make sure that I was emphasizing what was actually happening. All I'm saying is, okay, for example, if you're going from a 0 to 1, all right, if you go to a 1, the NMOS device is off, right? So that switch down here is off, and this switch is on. So therefore, it's this R that's part of the circuit. Right? Is that clear? Okay. I just wanted to make sure, just in case, because otherwise you'll see 2 R's, and then you're going to say, where did Stan choose that R from? Is that from the NMOS device? Is it the PMOS device? And I also wanted to emphasize it's depending on if it's a rising or falling input, a different transistor is actually contributing to the current or to the output of that signal. So I just wanted to make sure that you guys are aware of that. That's what I'm actually doing. Okay, now a little bit of fun. Okay, so suppose, and you can work this out. So suppose you had a unit transistor on a 65 nanometer process, and you can actually work all this out. But suppose I told you this, right, and that the resistance was 10 k ohms, and the capacitance was 0.1 femtofarads. What's the maximum speed that you can get for a fan out of 4 inverter? And by when I say a fan out of 4, is this situation. How fast can I run that? Right. And what we've seen here is, in this particular case, if you're looking at an inverter, right, and you've sized it as the way that we've just described it, the falling and rising edge are equivalent circuits, so you don't need to worry which one of these you choose, right? Because the rising or falling edge, the propagation delay is the same, but it's not always the case, right? So if that's not always the case, and you want to work out how fast you can run a circuit, how would you determine that? If they're the same, it's easy. You choose one, you do it. If they were different, the propagation delay, going from a 0 to a 1 is different to a 1 to a 0. How do I work out how fast I can run that circuit? What would dictate that? Maximum value, right? Yeah, yes, the maximum propagation delay, right? In this particular case, I'm just trying to emphasize that there are differences. So even though I'm writing this example down, don't take it as, there's more to it, right? And that's what I'm trying to emphasize to you. Okay, so yeah, you would choose the maximum value. And in this particular case, what we said, it's an inverter, and I've chosen the PMOS and the NMOS so that they're giving me the same value. So I can choose either, the two circuits are equivalent. So I've got the resistance due to the diffusion, and then the resistance and the capacitance due to the diffusions. And then since I'm driving 4 gates, and we know each gate has a capacitance of 3C, so therefore there's 12C. So all up, I've got 15C times R, right? And in this particular case, I've taken the log 2 in there, right? And that's why I'm doing the propagation delay. And usually what people do is when they're doing the propagation delay, they just go RC. But they've actually modified the R so that it already takes into account the log 2. What you can actually show is you do the calculation, so you've got 150 times, so 50, sorry, it's supposed to be, what did I do here? Okay, so 15 femtofarads, okay. All I've done is 15 times 10 times 1,000 times 10 to the minus 15, right? So really, it's 10 times 10 to the 3 times 15 times 10 to the minus what?
12.
No, femto. Femto is 10 to the minus 15.
0.5 times 10.
Sorry? 15. It's not 1.5, it's 15.
Because
Uh,
C is
C is
0.1.
Yeah?
So the 15 times 0.1 is 1.5.
All right, so I've made a mistake. Okay, cool. All right, good. Now I think, have I made a mistake? Okay, 10K, and what did we say? It was 1.15, so so it's 1.5 femto. So it's 15 times 10, so it's 15 pico.
Yeah.
All right, so 15 pico, and then you can work out what that speed is, and I think it turns out to be roughly about 66 gigahertz. So what it says to you is, you know, if you're not as bad at arithmetic as I've just proven myself to be, that if you had an inverter on a 65 nanometer process, which was driving another 4 inverters, that the speed would be, that you could run it at, is 66 gigahertz. Pretty impressive, right? So you can get these circuits switching on and off at 66 gigahertz. Pretty cool, eh? No, people aren't impressed. I mean, I came from an era where, you know, megahertz was impressive, right? So 66 gigahertz is phenomenal, all right? Now, but anyway, this is showing you that there's multiple ways to build very fast circuits. So what is the key takeaway here? If I was saying to you guys, I really want you to build me a very fast circuit, what would you do? What are some of the important things?
Make sure the propagation delay is small.
Well, yes, because that's what I'm saying, but that's the part of the lecture. But what would I do if I said to you, if I was your manager, suppose you were working for me at AMD, as an example, and I said to you, I want you to build me a processor that operates at 5 gigahertz, right? And you go to me, yeah, okay. And then I said, look, you know, I really can't afford the 25 million or 30 million 7 nanometer mask set. What did you do it at 130 nanometer process? Right? What would you say to me? Okay, what you would say to me is, well, I don't think I can do it. and yes, you're still saying you've got to pay your 25 million in order to get a mask set, and then I'll say you better make sure that it works. But that's only the mask set. The process costs about, in order to develop a process, about $750 million. But what we would say is, in order to increase the speed and having a high probability that we'll be able to get high speeds, what you want is the transistors to be as small as possible. And the reason why that works, capacitance is much smaller. Right? Now the resistance goes up, but the capacitance is much smaller. Right? So that's the advantage that you have. All right. Good. So we're learning a little bit about high-speed electronics. Good. Now, where there's a lot of things that people get confused about is that if we've got the same transistor of the same type, right, and they're in series, and can someone think of an example where you might have 3 transistors in series? A gate that has 3 transistors in series? You can probably press next on your slides and you can probably see it, right? It's a 3-input NAND, or multiple NAND, right? And a 2-input NAND would have how many transistors in series? 2. Okay. Anyway, we'll show you an example. But the point here is, so far what we've been doing is we've been looking at these transistors. For example, when we were looking at these transistors, and we said there's, if this is a PMOS and an NMOS, we said there's drain to substrate capacitance and drain to substrate capacitance and source to substrate capacitances, right? Now, and essentially, what we're doing here, can anyone tell me how they would expect this NMOS transistor to be built? We went through it in one of the lectures. All right, so if we were building it on a bulk substrate, what did we do? So we had a lightly doped P substrate, and we had an N-well right here. We had another N-well here. And we had the oxide and the gate, right? And then we had the contacts, right? We talked about this briefly, if you remember. What I would suggest is you also, if instead of looking at the footy on just before the footy or maybe after the footy on Friday, spend a little bit of time just to open up a book on the CMOS devices and look at how they actually fabricated. But essentially what we did here is we said, if we've got a transistor, this is the structure, right? We've got an N-well, an M-well, we've got the oxide, and essentially what we said is this has got this, these capacitors, right? And we said that there's a set of capacitors here and a set of capacitors here, and then there's also capacitors in the gate, etc., etc., etc. But what actually happens is if we've got multiple transistors of the same type in series, in order to make your circuit run a little bit faster, and you see this in a lot of textbooks, but they never tell you why there's this one capacitor is missing, one set of capacitors are missing, and you're always there scratching your head thinking, where did it come from? Like even the book, the VLSI book that I've asked you to refer to occasionally, you ask yourself, where does that come from? Why is there a set of capacitors missing? And essentially, sorry, I'll have to use the same paper because I've run out of paper. Essentially what you're doing, you got another one? Okay, great. Okay. Now even a few pieces of paper. All right. Essentially, what you're doing is you got an N-well, an N-well, an N-well, and what you do is you got the gate and the gate, and you're actually sharing this well, N-well. So you get N-well, N-well, N-well. So you share this N-well, right? And as a consequence of doing that, you can think of it as each one now has half the capacitance, but because they're in parallel and whatever, you got just essentially you've got half the capacitance. You don't twice as many capacitors, because really, as we were talking about previously, if you had two different contacts, contact coils, you'd have to put another capacitor here and you'd have to put another capacitor here. Right? So you're saving yourself a little bit of capacitance as part of the layout, which actually allows you to actually run, reducing the capacitance, so therefore you can actually run the circuit a little bit faster. And that's all I'm trying to emphasize here, that if you've got capacitors of the same type and they're in capacitors, if you've got transistors of the same type, what you do is you essentially share these wells, right? And as a consequence, you now have at these junctions, you've got essentially the half capacitance. And what I'm trying to point out is if you're doing a layout on a chip or on a substrate, do not do what you would like to do, which is draw a capacitor, draw a transistor, connect it with a bit of wire, draw another transistor, connect it with a bit of wire, right? Because here it's got twice as much capacitance at these junctions, right? Here I'm sharing it, half as, this point here has got half as much capacitance. Make sense? All right. That's, I mean, the reason what you might say to me, Stan, why did you confuse me? Why did you spend, some time going through this? It is because a lot of people on a lot of lecture notes and a lot of books actually all of a sudden begin leaving out this second capacitor and people start getting confused. And I just wanted to make sure that you knew why it's been omitted, right? Because I can guarantee if you look through the book, you'll look at it and you'll be like, where did that come from? Why is it wrong? Well, there's wrong. Stan, two things. One is you'll probably come to me and say, Stan's you made a mistake, you left this off. And the other thing is you'll go look at some manuals or some books and you'll be like, oh, geez, it's not there either. What's going on? All right. So now let's look at this 3-input NAND gate. All right. And what we've got is we've got these two PMOS transistors, three PMOS transistors, and we've also got these 3 NMOS devices in series, and in this particular case, and for good reason, I've chosen the NMOS devices to be 3 units large and the PMOS devices to be 2 units large. And the reason is, at any one time, you're driving through one of these, one of these PMOS devices, and always you're driving through these 3 NMOS devices. So I'm doing this so that I can actually minimize the resistance through this. And this is usually one of the ways that you do what you do in order to design these 3-input NANDs, or even if you did a 2-input NAND, you'd go 2 and 2. Anyway. So here, what I'm asking you to do is to annotate all the capacitances. So we've got the gate capacitances, the diffusion capacitances, and just to emphasize, because these are in series and we're using the same diffusions, we've only got one set of capacitors here, like 3C, 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 and 3C. So what we can then do is we can sum up all the capacitances, so we can see at the input of the gate, each of these gates or these inputs, we've got 5C of capacitance, and at the output we're driving 9C, depending on if the NMOSs are on or off. Because if they're on, right, we're not only driving 9C, we've also got to look at the resistance and these other capacitance that this output node might actually see. All right, so what I'll do now is let's go through, and because I was finding it too difficult to recopy this circuit so many times, what I decided to do is say, well, I was going to be brave and try to do 3 input NAND, but I was just getting it wrong and wrong and wrong. I thought, well, you know what I'm going to do? I'm going to go to a 2-input NAND. Still illustrates the point, but makes it a little bit easier for me, especially given how terrible I am at drawing. And And what I'm asking you here, and what we're going to do in this example, is work out what the propagation delay is going to be for a 0 to 1 transition and a 1 to 0 transition. And essentially what I'm asking you to do is to determine that for a 2-input NAND driving n identical gates, and here what I'm saying is n NAND gates. Okay? So how would we do that? Well, you know, if we look at this, and if we've got a NAND, and I've drawn a NAND gate here, and I know that, you know, I'm going to have the PMOS as being 2 units large, because there's 2 NMOS in series, and I want the total resistance to be R here. Each one of these is R, and R as through the series circuit, I'll make these twice as large, so that'll be, so therefore the resistance through each one of these is R1 and R2. The capacitance here is going to be, the gate capacitance is going to be 2C, as we would expect, and there's the appropriate diffusion capacitances. So there'll be 2C there, there'll be a 2C there, right? So let me draw it in. I've already put that one in there. There's a 2C here, and geez, there's supposed to be a 2C there, right? But it's not 4C. Why isn't it 4C? All right, good. Okay, good. All right. Now, what I want to do is to work out the propagation delay. So, what I've said is, let's look at what's the worst case for a rising edge, right? So if we're going through a rising edge, right, and it's a NAND gate, the only time that occurs is either when we've got, there's actually 3 cases, right? So it's either A is 0, B is 1, A is 1, B is 0, or A is 0 and B is 0. Okay. So let's look through the worst case, and what we can actually see is, if you go through this, one of the worst cases is when one is on and the others are off, in terms of these 2 inputs. And if we draw the equivalent circuit, what we can actually see is we've got the resistance through the NMOS being, you know, up to supply being R, and then we've got 6 units of capacitance on the gate, plus 4 in C, where that's the capacitance that we see looking into the next set of gates. So therefore, the rising delay is going to be R6 plus 4 in C, right? And in this particular case, I said, yeah, we're driving in identical gates. So that's the rising. And we can do the same for the falling, only now that we've also got, you know, if we're looking at the falling, we've got to look at both the NMOS devices being on, the PMOS devices are off. So we've got the capacitance of the other 2 gates, the capacitance that the diffusion capacitance at this node, at the output node here, right? The resistance through the first NMOS, the capacitance due to that diffusion, and then the R2 again. Now, why have I done this? I mean, this is the equivalent circuit. Well, what I'm trying to do here is actually get you to use the Elmore delay theory or methodology. So what we've got is, you know, if we're going through, you know, we're going to 0, what's the output? We've got R2 times 2C plus R2 plus R2 multiplied by that capacitance, right? That was the, if we remember, it was RICI, yeah. Right? And what we looked at is the node and the leaf, and then it was the total resistance to that node, right? So in this particular case, for the falling edge, that's the propagation delay. So what we can see here is that the falling propagation delay, or the two input NAND, is slower at going from a 1 to 0 transition than it is from going from a 0 to 1 transition. Okay? And so this is the ratio. It's not much different, but it is one time constant slower, right? And if you were, if you were driving 3 gates or 2 gates, what we could do is, if n equals, in this particular case, I'm assuming I've got 3 gates, all right, and I'm driving another 3 gates. What we can actually do is work out the ratio of the falling to rising, and we can actually see it's 19 on 18. So it's a little bit so raise is slower than fall time. All right. So that actually now allows you to go through and to calculate, the propagation delay for a NAND gate, a 2-input NAND gate. Now, one of the things that I wanted to also talk about is, I've been talking about this magical effective resistance, and it's usually given to you, but one of the things that you might want to do is also work out a way to calculate it, right? And one of the simplest ways to actually go through and calculate it is to work out what the effective resistance is and look at it as being the average value of VDS on the IDS during a switching event, right? And the way that you would do that, if somebody just gave you, if they didn't tell you what it was for a particular process or a particular transistor, but they gave you the IDS versus VDS, characteristics, you can actually work it out, right? And for an NMOS device, the way that you would define it is the current is defined at the start of the transition, which would be when VGS is approximately VDD on 2. So that's VGS and VDS is VDD. And the high transition, or the high end of the current at high, is defined as VGS equals to VDD and VDS equals to VDD. Now, what you can actually show is, well, it's essentially the gradient of this load line. I've got my current when I'm out, an output of 1 volt. I've got my, I want to work out my current when VGS is 1 volt, but my output voltage, or VDS is, or my VGS is, so VDS is half. What you can actually do is work out what that gradient is. And that will give you the effective resistance. So you can actually work it out. So if I gave you your IDS versus VGS versus VDS graphs, you can actually work it out. Right, so maybe in a test or an exam I said to you, well, guess what? You found some transistors on the road, and there was a data sheet, they were attached to a data sheet. How can you make them switch? What's the fastest NAND gate that you can build, or inverter that you can build? Well, this gives you the ability to work out what the resistance is at least, right? All right. Now let's talk a little bit more about delay. And what we'll do is, there's a couple more slides that I wanted to go through. How are we doing for time? We've got a couple more minutes. Can I have a couple more minutes? Yes? Have you got a lecture next? All right, so what we'll do is we'll do it on Monday. All right, so what I wanted to talk about is, I'll try to go through it quickly on Tuesday. like not next. So they'll be in 2 weeks time. Look at linear delay. Okay, homework. All right, homework. Look at these. Have I got them on the? I might not have them online. I'll put them online. What I want you to do is look through these, and what I'll do is I'll go quickly through them in our next lecture before going on to the next stuff. All right. Now, what's this super exciting lecture that's better than this one that you're going to go to?
Communication network.
All right, guys, let's continue. Okay. All right, guys. Have a great football day off, and then next week enjoy yourselves with a bit of revision. And I'll see you in about, what is it, a week and a bit's time? 10 days.
Well, those two equations seem too different.
It's IS, right? IS is the sum of all the resistances. That's what I'm trying to say. So it's not. Got it? Okay. Sure. All right. Okay. So here. All right. So let's look here. You've got 2. This one's got 2. There's another 2. And there must be another 2 there. There's 6.
Yeah.
Plus looking down there is 3. 9.
Oh,
Okay. Don't tell me I made a mistake because I don't want to hear it. Okay. Yes.
Why we have gate capacitance here but not in this case? Is it you don't
No,
have
we do have. We do have. I just haven't drawn it. Yeah, there is gate capacitance. I just haven't drawn
so
it.
there should be more capacitance.
No, there's. No, okay. So there's this, right? So there's 3 of them. So what's the capacitance? So hopefully I haven't made. So it's 3C. This one's 3C.
Yeah.
Plus 3C plus 3C. What have I written? So 3C plus 3C. Yeah, that's right.
Here's 2C and here's 1C.
Oh, no, but you don't see this through. This is the gate. So in the gate you're only seeing this. You don't see through the gate. You only see the gate.
Only see the gate.
Okay. So what you're doing? Okay. Let's. We got a text this one. Let me grab a text. So what are we actually inverters? All right. I had an inverter. All right, and it's driving another inverter.
Yeah.
All right. Okay, let's do this. All right. What did we say here? We said, well, there's a capacitance 2. There's a capacitance, and say this is 2 and this is 1, right? So 2C. There's a C. Oh, sorry. Yeah, no. 1C. 2C.
Yeah.
2C. Right. But this one doesn't contribute.
That doesn't count.
Yeah.
You have to connect to the
Yeah.
VDD.
And this one, so it's 1C. Right. So this, and now this is seeing 1C plus 2C. You don't. If this is just driving this, right? It depends what you're. If you're trying to work out here, how fast can I move this? Right. What's my total capacitance? Well, I'm not looking at the output. I'm just trying to work out how fast can I drive this. That's all I'm saying. I'm not saying to look at the output here. I should have made it more clear. I see what your question is. You're asking, what do I do? What happens here, right?
What I mean is there should be another 2C here.
There's a 3C here.
Oh yeah, 3C.
Yes.
Yeah.
There's a 3C there. There should be a 3C.
Why we don't consider the input gate capacitance?
Yeah, that's what I didn't wire.
If we do, there should be a 2C and a 1C.
Here's 2C.
Yeah.
At the gate.
I know there's 2C and a 1C. there's a 2C, there's a 1C, all right.
What I mean is that there should be another 2C in here.
Another 2C.
Yes.